back at it for Chapter 2 of CCNA3. Alright, LAN redundancy. I'm going to tell you guys right now, this is a long chapter, and there's a lot of stuff going on. So you'll probably want to break this lecture into several different sets, okay? Anyways, so what's it called? LAN redundancy. And so what we're going to go over today basically is spanning tree, alright, the changes in spanning tree, this thing called PVST, which is per VLAN spanning tree protocol, which is a Cisco proprietary spanning tree, all the stuff that has to do with it. Then we go into this rapid PVST, which is a newer, faster version of spanning tree. Then we're going to look at issues, apparently, right? Describe first hop redundancy protocols, which they sometimes put into the acronym FHRP, which has to do with these things down here, HSRP and GLBP, and there is also VRRP. Okay, those are all first hop redundancy protocols, and what those are doing is giving us a virtual default gateway so that if, say, our router goes down, we can still get to the internet through another one, or yeah, a redundancy on our critical internet connections there. Okay, so let's get on it. Yeah, we're not doing stormy traffic. Okay, redundancy at the OSI layer 1. Okay, so what we're doing right now is we have all these switches connected, and you guys are familiar with what we're going to be talking about here with spanning tree, because spanning tree is that thing that makes our switch ports become orange when we first plug a cable in, or when we first plug a network in. And so let's see what they want to tell you about redundancy. Probably that if a link goes down, you can still get to somewhere else. Alright. Oh wow, look at that. Yep. Okay, well that worked good. Alright. Oh wow. Great. Now it's broken. Okay. How are we going to get there? Oh, the switch detected it. Alright. Alright. Yeah, woo! We're all good. The redundancy's great. Okay, so things to consider when implementing redundancy. Let's see what they say. MAC database instability. Instability is the content of MAC address table results from copies of the same frame being received on different ports of the switch. Data forwarding can be impaired when the switch consumes the resources that are coping with instability in the MAC address table. Okay, broadcast storms. Without some loop avoidance process, each switch may flood broadcast endlessly. This situation is commonly called a broadcast storm. When we do a lab for this chapter, what we're going to be doing is creating a broadcast storm, and one of our packet tracer activities actually has the ability, like, I don't know, a bunch of guys last semester created a broadcast storm in packet tracer, which I didn't know was a thing. But what it basically does is makes your switches useless. They don't know where to send anything. Multiple frame transmission. Multiple copies of unicast frames may be delivered to destination stations. Many protocols expect to receive only a single copy of each transmission. Multiple copies of the same frame can cause unrecoverable errors. Alright, so we're going to have to send them again if that happens. Alright, so that's our redundancy. Okay, so let's see what our MAC database instability is. Alright, here we go. Oh, we're sending a broadcast. Oh, it's mapped to F01. We know that from the MAC address table. Oh, we need to send it. Alright, so looks like our MAC address instability caused a broadcast. I don't know. I've never actually caught this one in the real world. Anyways, I have had problems with broadcast storms in the real world. They're pretty exciting too. Just take down an entire switch in no time. So let's see how Cisco plays this one out. Oh. Broadcast. PC4 forwards out a new broadcast that also gets caught. Oh, but there's still broadcasts going. There's too many. Oh god. And then your RAM fills up and your switches crash. Alright, so it's just looping and crazy. Oh man, it's insanity here. Anyways, that's how it feels in real world. How do you know when a broadcast storm is happening? Usually on a Cisco device, all of your ports start turning orange and flashing really fast, or they're green and they're flashing insanely fast. So anyways, we will do that in class. Alright, so our final problem, duplicate unicast frames. So it sends it to S2. Alright. There's no record of PC4 in the MAC address, so it floods the unicast packets out, all ports, except the one it came on. Well, that should have been bad, because it flooded out that one. It shouldn't have been there. Alright. So it receives two. Neat. Feel free to read more on those. Okay, so spanning tree algorithm. Spanning tree algorithm, if we didn't have it, these loops would cause these problems that you've just been seeing. Alright, like it would just, there'd be non-stop floods because we have no way of saying, hey, don't send it out here and here. And we don't know if this switch is going to send it this way or this way, right? And so that's what causes these problems. So let's see what Cisco says about this. But basically what spanning tree is doing is it blocks one of the redundant ports so that it will stop the loop. Okay, so a routing protocol, right, its goal is to find networks and not have loops. Alright, so spanning tree is like a routing protocol for layer 2. It stops loops. But instead of being layer 3, it's layer 2. Alright. And so now what they're going to show, I'm sure, is now that this one failed, this spanning tree link will come up. Spanning tree was blocking this port from sending, and so now it's not going to. And so if this was blocking, I'll wait till this is over. But yay! It worked even though the trunk went down. Okay. So when that was blocking, how we would know it was blocking is this port would actually be orange on the switch, and that's not a bad thing. Like, you know, so first when spanning tree comes up, it runs the spanning tree algorithm. That's that orange that you're seeing. And then it's going to block one if there's two ways. If there's redundant links in this network. And so, or we hope it's going to, so we don't get a loop. And so if this one's blocked, it's going to be orange on this side and green from this switch. So that's how we know it is a blocked port. Alright. So port roles. I don't know how to tell you this is that important. It's important for finding loops. That's the only reason they're telling you about this. Okay, so support roles designated means that it is a forwarding port. Okay, so a root port is different. We have a root bridge. Okay, so the root bridge is like when we have OSPF. Spanning tree and OSPF are very similar. And so on OSPF we had our designated router. Okay, well, and that was the boss. And so in spanning tree, we have a root bridge. And the root bridge is well, we're not talking about what it is yet, but it's the boss. Okay, so we'll talk about how it's assigned in the next coming section here. But spanning tree, the root bridge, one way to know it's a root bridge, like you'll get Cisco questions that'll tell you, for one, if you did show spanning tree, it would tell you it was the root bridge if it was the root bridge. But another way, if they blur that out, which they're known to do to see if you know that it's the root bridge, a root bridge always has a designated port. So see how both these ports are designated to these switches? Now if we look, every other switch has a root port. Okay, so the root port is the port that points to the switch. Okay, now how is this decided? Well, it's faster for this switch to get to the root bridge through one hop on it's fast Ethernet, so it's 100 meg, then going 100 meg down here, and then 100 meg up to here. Okay, and same with here. This is the root bridge, one hop instead of going around. And so that's how spanning tree chooses what to block, is because then we know this is going to be the block port because it's the alternate port. Okay, so it's the backup port. This designated one's forwarding. So if we see designated or root, we know they're green. Okay, so they're green and forwarding, whereas an alternate is blocking. And so this alternate port is actually established by root bridge priority, and so this port priority is going to be lower apparently than this one, and that's why it was chose to be blocked rather than these. And it's easier to see if we had like 6 switches out here. It's easier to pick up on the alternate port because the root bridge will be right there, and you have 6. The further away you get from the root bridge, the easier it is to decide. Right here, none of them are that far away, and so deciding here and here is based on, well, just as all layer 2 things are, right? Probably on the MAC address of these switches, because, spoiler alert, that's how we determine root bridges in the days of old. Alright, so now we're back on the root bridge, and this is kind of showing what I was telling you before. Well, actually it's showing the priority, and so we can set the priority. I believe the default is this 32769. Alright, and so maybe you guys remember from OSPF. OSPF likes to elect the highest number. It's layer 3, right? It's higher up than layer 2, and so OSPF likes the highest number, right? So we're going with the highest ID or the highest IP, whatever it is that adds together. We want the highest number, right? Well, spanning tree is the opposite. It wants the lowest number. So 32769 is the default, and so we know this is the root bridge because somebody set the priority lower than the default, so we don't even have to look at the MAC addresses because the priority is going to enable this switch to be the root bridge. On the other hand, the reason they're showing this priority is if it was just doing it by default, it would actually do it on, so if we all had the same priority like normal, it would go on the lowest MAC address. So actually this would be the root bridge, because if you look, this MAC address is much lower than these other two. Okay, so anyways, priority is one way of selecting the root bridge. And so this is how we get our bridge ID. Alright, so we do the bridge priority, the extended system ID, and the MAC address combined, and we get our root ID, I guess. So yeah, I guess, is there anything important to talk about there? Anyhow, we're gonna move on. So, spanning tree. this this has to do with the ports. Okay, so remember OSPF? This is where I meant OSPF is the same. Remember, OSPF runs on cost. Spanning tree also runs on cost. And so if you look here, the higher your speed, the lower your cost. Okay? And so what this is going to do is we could set the cost. And what setting this cost on this port would do would be we could actually form, like, we make a port an actual root port, or we make a switch a root bridge. Alright, so yeah. What else is cool about the port costs? Port costs can be set from 1 and 200 million. Anyways, we'll just keep going and see what else it has for us. How the cost would be set otherwise would be based on the speed, and so on the switch, we take the speed and then the MAC address, and each port gets its ID because its MAC address would be +1, so 00A001111 +1 would be F01. F02 would have a higher cost because it would be +2, and so on and so forth. So if you're not changing your port cost, your F01, F02 are going to have a higher priority to the root bridge than, say, F011 would have a much, or F018 especially. You would have to have no other link there, and so that's one of the silly things with spanning tree. Alright, so now with port role decisions with RSTP. Okay, so RSTP is Rapid Spanning Tree Protocol, and so it's similar, except it's just faster than the old spanning tree. And so let's see, we have root ports, designated ports. I believe there's edge ports as well. Maybe they're going to talk about edge ports. No, still alternative designated. Basically the stuff we're going on, but RSTP also does, if we're going to a PC, that's called an edge port, because it's where it's out of its spanning tree. Anyways, keep going and see if it brings it up later. Back to designated and root and alternate ports. Oh, just want you to determine them. Yeah. Kind of talked about that already. Feel free to read that. BPDU. Okay, so BPDUs are bridge protocol data units, and so that's what actually all the information, whenever we have a trunk link, right, BPDUs are propagated, and that's where we're getting information. BPDU, each switch port is going to send out that BPDU. Let's see what else it says about here. Well, feel free to memorize. I don't see a reason for it, but anyways. So here's our BPDU propagation end process. Okay. So initially, all switches think they are the root bridge, right? Because they don't know anybody else. Okay, so then BPDUs start sending bridge IDs and the root IDs out. Okay, so they're all going to compare, and before we even do anything, let's just have a fun little task of finding our root bridge and our root ports. Okay, so our root ID is going to take the lowest, which we can see it's S1. So if I was a bet man, I would say that S1 is going to be my root bridge. Okay, and so based on this, my F01 is going to be, you guessed it, the root port, because the root bridge, how a switch gets to a root bridge, is the root port. Okay, then we go over to here. What's F01 going to be? Root port. Okay, S1, F02. What does a root bridge only have? Designated ports. This is designated port, this is designated port. Now one of these is going to be a designated port. So how are we going to find that? We're going to find it by our bridge ID again. So whichever one is lower. And so this F02, I see that it has a higher bridge ID. And so it is going to be the blocked port. And this is going to be a designated port, or this is the alternate port, I guess. And this is the designated port. So yeah, that's what the BPDU process is doing. If you want to look through these figures and go over it, go ahead. Alright, so here they're showing you the bridge ID, and so in the olden days, or I don't know, this kind of is PBST from what I can see, but this used to be your spanning tree election. You just do priority and MAC address. Now with Cisco's PBST that we're going to talk about, it actually puts in the VLAN information, and so you have bridge priority, VLAN information, and MAC address. Okay, so now it's going to show, so your bridge ID, this one's based on priority, as we can see, 32769, default, lower than default, so this is going to be the root bridge. Now MAC address, as I said before, S2 has the lowest MAC address, and so it is going to be the root bridge for spanning tree. If we're not using priority, if we're just using the default priority. You might want to try it out to make sure you understand designated root ports back on those last ones, but we're going to move on to types of spanning tree, right? And I guess I'll just read you these ones. Well, I'm just going to go straight to, I guess, we'll do 802.1d. The legacy standard for bridging and spanning tree protocol. Okay, and this legacy one, when they created it, they did not have more than one VLAN, and so it was made for just VLAN 1. Okay, CST assumes one spanning tree instance for the entire bridge network regardless of the number of VLANs. Okay, it's based on that same thing. PBST plus. Okay, a Cisco enhancement of spanning tree that provides a separate 802.1d spanning tree instance for each VLAN configured in the network. So PBST again stands for per VLAN spanning tree protocol. Okay, so you can just call it PBST. Alright. So 802.1d 2004, an updated bridging and STP standard. 802.1w. Okay, and sometimes they will ask you 802.1d. You'll probably get a test question that'll have these standards in here, so wouldn't be a bad thing to memorize 802.1d and 802.w, and you don't need the S, but anyway, so 802.1w improves convergence over the 1998 spanning tree protocol by adding roles to the ports and enhancing the BPDU exchanges. Alright. Okay, rapid spanning tree PBST plus, a Cisco enhancement of RSTP using PBST. And 802.1s MSTP maps multiple VLANs into the same spanning tree instance. Okay, where we would use this is PBST can only have so many VLANs on it, and so if you had thousands of VLANs, you would have to start doing MSTP. And there's also an MSP, which just allows you to put a whole bunch of these standard 802.1ds together. So, do they have it here? They don't have it here. Anyways, feel free to read through these if you want a little bit more, but I believe we're going to go over them right now. So, spanning tree. Low needs, slow convergence, okay? And this is actually, most of what we've been seeing is rapid spanning tree on our switches. And so, old 1998 spanning tree took about 60 seconds, I believe, to converge. And it actually doesn't say right here, but I believe it was 60 seconds. And then PVST Plus, why does it need more resources? Because you have more VLANs, right? STP is based on one VLAN. This PVST Plus is going to base it per VLAN, okay? And what I mean by one VLAN is you're going to have one root bridge to rule them all. PVST Plus, we can have different switches being the root bridge, and I will kind of go over that in a little bit if we get the right graphic. Okay, so RSTP, well, we've talked about that. Medium resources, rapid PVST, lots of resources, MSTP, high. And this one, MSTP, and MSP is an open standard. This MSTP is a Cisco standard. So, all right. So with PVST Plus before, this is kind of what I was talking about. We can have a different switch be the root for VLAN 20 as for VLAN 10. So say all or most of our traffic for VLAN 10 is over here. Like this is the main building for VLAN 10. That's why we'd want to make this the root bridge for that, whereas most of VLAN 20 is located over here. We'd want it to be the root bridge over here. But maybe we have a few people here, but if we, by splitting these up, we can kind of shape traffic to go in a more efficient path just by picking the root bridges. Alright, so these are our port states: blocking, listening, learning, forwarding, or disabled. Okay, so disabled is just off, and these are based on just straight PVST. They're similar to spanning tree original. Alright, so listening and learning. So what are these doing? Listening is listening for BPDU, like receiving BPDUs, and what's it learning in those BPDUs? After it starts receiving those, it's going to go to learning. And so learning's where we actually start learning MAC addresses. Let me make sure we're doing this right. So listening for the path of the route. STP has determined that the port can participate in the frame forwarding according to the BPDU frames that the switch has received. The switch port receives BTU frames, transmits its own BTU frames, and informs adjacent switches that the switch is preparing to participate in an active topology. Learning learns the MAC addresses the ports prepare to participate in frame forwarding and begins to populate the MAC address table. And then we go into forwarding. So forwarding is when we're in the green state. So if in spanning tree, all three of these are going to be orange, right? It's going to start out blocking. This port is an alternate port. It does not participate in frame forwarding. The port receives BPDU determine the location and root ID of the root bridge switch and which port each switch port should assume in the final spanning tree topology. Alright, so it's just blocking there. So when we turn on our switches and they start receiving, so that's listening. They're starting to go into the spanning tree protocol. And so this is where the algorithm starts. And then once it's determined the root bridge, it starts learning the MAC addresses and of its neighbors. Then it goes into forwarding, and you're good to go. Okay, so disabled. The layer 2 port does not participate in spanning tree and does not forward frames. The disabled state is set when the switch port is administrated disabled. Okay, so that hopefully makes sense. So what port states actually, you will probably always see ports in forwarding or blocking unless you do a show spanning tree on them, unless you're having an error or they are red as they're firing up. Otherwise you're going to be in forwarding or blocking. Blocking would be orange on one side, green on the other, because one side would be forwarding to the blocking port. The blocking port is going to be in that alternate port state. Okay, and so these states have to do with PVST plus or with spanning tree. Okay, we're going to change a little bit when we get to rapid. Okay, and so we've kind of talked about the extended ID with PVST, right? This is where we're picking a extended ID has to do with picking a root bridge for a certain VLAN. So then we get to rapid spanning tree. Okay, so port states are looking similar, right? It's based off a similar technology, but hopefully it gives us our states here. Well, I don't know if it'll give us that better, but with RSTP we don't, as you can see, there's no listening state. Alright, so there's a learning, a forwarding, and there should be a block, but I'm not seeing the block either. Let's see if we can go to the states. No. Well, anyways, so rapid spanning tree drops the listening state, and listening and learning are combined into the same state with rapid spanning tree. Probably the reason it's faster. Alright, so edge ports. This is a new type of port. Remember, we had designated, alternate, and root. And so now these ports that go to, this would be probably a database server, and these are end clients. They are going to be edge ports. So edge is where it's just a client. They're represented on the Cisco. This is Cisco proprietary command, but it says spanning tree port fast. And what a spanning tree port fast, when we make that edge port, it means that there's no way there's spanning tree there. It's a host, and so instead of it skips the learning phase, it just goes straight to forwarding. And so anytime you see spanning tree port fast, it's going straight to forwarding, and port fast is also indicating that it is an edge port. Alright, other change with rapid spanning tree is we have point-to-point and shared. So if we actually looked at these links, they would tell us whether, so this is going to be a point-to-point and this is going to be a shared, I believe. Nope, I'm wrong. Alright, so point-to-point is actually when we're running in full duplex, and shared is if we're on half duplex. So I guess our shared would be right here with the hub. That'd be shared spanning tree, and these would be full or point-to-point. Anyways, edge port, root to port, alternate. Just talked about that. Okay. Alright, so this is the default switch configuration for a 2960. It's in PVST plus. You can run it on rapid if you wanted to, or I guess MSTP. I've done rapid PVST, but never MSTP. We know it's enabled in VLAN 1 because all ports are in VLAN 1. We have switch priority, as I've said earlier, of 32768 right here. Spanning tree port priority 128, port cost same as what we looked at, and anything else important? Alright, our hello time is 2 seconds, our forward delay is 15 seconds, and our maximum aging time is 20 seconds. Okay, so what does any of that mean? Well, I would have to say it has to do with your how long it's going to take before you can actually start forwarding on spanning tree. That's what those timers are. And when it's going to drop, right? If we go over 20 seconds, it's probably going to bring up hopefully your redundant link. Because remember, there's no need for spanning tree if we have, here, let me bring up packet tracer. Spanning tree, we only need if there's redundant connections. So because we want to remember that spanning tree is only stopping loops. And so if there's no way to have a loop, there's no need for spanning tree. So if we have something like this, you don't have to have spanning tree, right? Now, spanning tree will calculate. Now we'll show you. There's probably a blocking going on right after we add that in there. So it's going through this algorithm. We got orange port light, and we're sitting here waiting because they told us 2960s are on PBST plus, so we have a longer wait than if we were on rapid. And there we go. So now it's calculated. So we see how it's green on one side, forwarding here, forwarding here, forwarding here, forwarding here, forwarding here, and this orange indicates a block. And so if we're actually talking about these states and all of this stuff, if you want to see what I'm talking about, then we just say show spanning tree. And so we have a root port, right? It's a full duplex connection, so it's point to point. That's what that means. And we have a state of F02 is in blocking while F01 is forwarding. Now our port roll is alternate on that blocking, like I've been ranting about happening. So anyways, I'm just trying to show you where these words actually matter in the real world. Alright, so now if we don't want to set the priority and we want to make something a root bridge, Cisco gives us another priority, and it's this command spanning tree VLAN1 root primary, and we can actually do root secondary. Okay, and so this guarantees we know where our root bridge is. So if we're primary, it will always become the root bridge. If we're secondary, it'll become the backup. This is the spanning tree way of having just like OSPF has a DR and a BDR. Primary is the DR and secondary is the BDR for spanning tree. So if this goes down, we can go here, and so we can plan for a system fail in that manner, because I hope you guys are gathering that the root bridge, it's going to block not going to the root bridge, and so all traffic forwards. It's like all rivers run to the root bridge. So wherever the root bridge is going to be the fastest way to get traffic to somewhere. So I hope I've conveyed that. So let's go back and see what else we have here. Just showing you some root bridge commands. Probably go over some of these commands, try some of them. Okay, port fast and BPDU guard. So we already talked about port fast. That it just makes the interface go straight to forwarding. Okay. If we issue this command right here, port fast default, it would actually put all ports into port fast. Then BPU guard is a little different. BPU guard, what it's going to do is pretty much what the name. So what it is guarding from is it works with port fast. So as you can see, port fast and BPDU guard. BPDU guard is going to stop if we put a switch on here and this port actually received a BPDU, which it never should if it's in port fast, right? Edge port fast and making it an edge port means that it's connected to a host, not a switch. And if we were to put a switch on there and we didn't have BPDU guard going, it could form a loop because this is going straight to forwarding. And so if the switch was connected to here and then connected to here, it would be a similar scenario as this and be able to cause a loop because we are not going through our learning phase or listening if we're doing PBST plus, I guess. So what BPDU guard does is it shuts down a port if it receives a BPDU on a port that's enabled with port fast. Okay, and so now what else it's going to tell you is how we configure port fast, right? Which is pretty simple. We go in the switch, we go in our interface, and we just say spanning tree port fast. And then it's going to turn that on. If we want BPDU guard, we put in spanning tree BPDU guard enable. Once again, if we want to do the default command, it's going to be, I believe they're going to show you that. No, they're not. Alright, so if we want to do the default command, we would do it on the global configuration. We'd say spanning tree port fast default or spanning tree BPU guard default, which would automatically put all of our ports into that, which I would suggest never doing. It's easier to just put this command and do a range command or something like that. Okay. PVST and load balancing. Okay, so this is kind of what I was talking about when we had root bridge and traffic, right? When we make this the root bridge, certain things get blocked, and so most of our traffic, we're keeping certain traffic going certain directions when we separate our root bridges. And so that's how it is a load balancing mechanism, because if this is the root bridge, we'll say this port is getting blocked, and so all traffic's going to come from down from here and go straight to here, and if there's traffic over here for there, it would go to there. Now vice versa, for this one, most of the traffic's going to be coming from here and from here, and so we can actually design spanning tree to save network bandwidth by setting up root bridges correctly. Anyways, that's probably the most important thing about spanning tree is setting the root bridges up so that you are most efficiently using the resources that you have. And well, I guess also that it stops loops. So spanning tree mode. Okay, so this is actually the command to change it from PBST to rapid PBST, and it's showing you the command right here. Spanning tree mode, rapid PBST, would put it into rapid PBST, such as you can see right here. Apparently they're default setting it to a point-to-point link as well. And sure, I'm not even sure what this spanning tree clear detect protocols is. Probably resetting the spanning tree protocol. I'm going to let you guys go over analyzing the spanning tree protocol. What they're talking about in expected topology versus actual topology is that until you get out into a lab environment, especially if you're not setting your priorities and planning this thing out, that you could actually get a root bridge, right? By default, if we all have the same priority, we're going to go over a MAC address. And like I said, it's going on the lowest MAC address. And what causes the lowest MAC address? Well, that would be your oldest device. And so sometimes spanning tree, if we're not planning it out, can be a nightmare. In fact, you could go on forum posts and forum posts of people that just despise spanning tree, and that's why layer 3 all the way down to the axis is becoming popular, because if everything's layer 3, there's no need for this spanning tree stopping layer 2 loops. But in our 3-layered protocols with layer 2 at the access to the distribution, spanning tree is very important. Oh, the consequences of spanning tree failing, well, that's a broadcast storm or a loop or something like that. Those 3 errors we were talking about at the beginning of this chapter. Repairing a spanning tree problem, well, get your switches back on, I guess. Okay. So now we're going to get into HSRP, or actually, what was it? FHRP. First hop redundancy protocols. Okay, so in the picture you see we have redundancy, but this 10.10.2 was actually the default gateway, and so the PC, if that link goes down, the PC can't get there, even though, well, he should be able to get there, but apparently something's not working right. But through this redundancy, it should still be able to get to 10.2. But we have this beautiful redundancy, so we might as well use it. So maybe they're saying we're going to say the switch went down. So then we're really up a creek without a paddle. And so I came up with this router redundancy. And so this is what's actually happening in these router redundancies, is the forwarding router is a real router. The standby router is a real router. Okay, so this virtual router, it's just virtual, right? That's what it means. And so they both are this virtual router. And so when we make these default gateway redundancy protocols, what it's going to do is it'll change the MAC address. If this router goes down, this standby router will then come back up. And so these computers, even though they're forwarding, they think they're forwarding this router. Right now they're actually being forwarded out of here. But if this router was to go down, this one would pick up and they would still make it to the ISP. Now you will need 2 routers with connections to an ISP, or maybe 2 ISPs, but that's for a different day. So they're showing this router goes down, so the virtual router picks it up and sends it there. So feel free to go over these terminologies. And finally we get to the actual stuff that is doing this. So that was the idea of a first hop redundancy protocol, but the actual one we have, and this is Cisco proprietary, is HSRP. And so if we ever want to know if we are running HSRP, all we have to do is say show standby. Show standby means that we are running HSRP. So HSRP basic, just like what we just talked about on that virtual router. If one router is on standby, and so if the active router goes down, the standby router picks it up and starts forwarding. We have it for IP version 6, and then the non-Cisco proprietary is this VRRP. Okay, so Virtual Router Redundancy Protocol, and it does the same thing as HSRP and GLBP. It's just an open standard. And so then we go to GLBP, and so GLBP is another Cisco proprietary standard, and it's similar to HSRP, except you need a bigger license to use it, or newer devices to use it. And instead of being active, it says Gateway Load Balancing Protocol. So the active and the standby, instead of just having this router sitting there with the internet connection, it'll actually load balance between the two through your virtual router. And so, yeah, and so then we have ICMP Router Discovery Protocol, a legacy FHRP solution. It allowed IP version hosts to locate routers that provide IP version 4 connectivity to other non-local IP networks. The only reason I read that is I believe it is on a test question at some point. So there was this IRDP before GLBP and VRRP and HSRP, but HSRP, VRRP, and GLBP are, keep those in your head, and just remember, open standard, VRRP, HSRP, one rack router running at a time, GLBP, load balancing. So as I said, if you were looking to see if you're running HSRP, you do the show standby. State is active, means you're the active router. This is your virtual IP address, and the router that is waiting to stand by if you go down is 10.1.06, and so we have the group name of HSRP1. Those are the keys to the HSRP. As far as I know, HSRP is not in Cisco very much. If you guys are interested, come in for lab and we will set it up, or I believe we can even set it up on Packet Tracer, so send me an email if you're interested in setting up HSRP. Alright, so GLBP verification. Easy enough. Show GLBP, right? And now there should be something. It should say load balancing. I think so. We have load balancing right here, which, well, I guess if you did a show GLBP, it wouldn't show up unless, but if we look at our HSRP one, I don't believe there was load balancing. Yeah, see, there's nothing about load balancing. So even if they don't give you a show command, if you ever see this screen with the virtual IP and load balancing, then you know it is GLBP. Well, if you guys feel like setting it up, we got some GLBP labs, and I guess that was the class. So I hope I didn't confuse you too much. Just remember, root bridges are the boss. They're set up through cost, and they can engineer traffic, but most importantly, they stop layer 2 loops. Really read through that stuff. It is hit pretty hard on a lot of tests, but as always, if you have any questions, please email me or post it in the Net Academy discussion.